Okay. My name is Hai-Jun Liao. This is my second time to come here. It's a very beautiful place. So first I would like to thank the organizers to give this opportunity to present our recent work, differentiable program tensor networks. Our work has accepted by Kitaev, and our source code is also available at this address. If you're interested in this work, you can download it and try it for fun. And I also want to thank all my collaborators, and Professor Xiang, Lei Wang, and Jingguo Liu. Let me first briefly introduce the tensor network state. Over the past decades, tensor network has become a powerful tool to study many-body systems, such as frustrated magnetic system and strongly correlated fermion systems. Usually, the tensor network include three components. One is the tensor network network representation, such as MPS, mirror, and tree tensor network, and PEPs, and PES, and so on. And another component is the tensor contraction. For example, if we want to compute the expectation value of physical quantities, so we usually use some controllable approximate scheme, such as bundle MPS and CTMRG. And the most important component is the optimization of the tensor network states. Usually they include two classes of methods. One is the imaginary time evolution method. Other is the variational optimization method. But the optimization of tensor network is still non-standing problem. Over the past decades, people have developed many methods. For example, the imaginary time evolution method include simple update, class update, full update, and fast update, and loop update. And the gradient and the variational optimization include the Phillips proposed the method based on the CTMRG method, and the Rollins proposed the method based on the channel environment. Yesterday, Lance has talked about this. Usually, this variational optimization can obtain the more accurate results. The evaluation of the gradient usually is very difficult to compute. So this shows there are two methods to how to compute the gradient. As you see, because the tensor network usually the infinite tensor network usually contains the local tensor appears many times. So the energy is a highly nonlinear function so we have to consider many Hamiltonian contributions. So as you see, the gradient is very difficult to compute. This just shows for the nearest level interaction. So if we want to consider a more complex model, for example, if the J1, J2, the terms will be double. So this is very difficult. So is there any way to is there another simple way to compute the gradient? The answer is yes. The AD can automatic differentiation can help us to do this tedious work. The idea is very simple. The idea is the AD just map the calculation of the gradient to a computational graph. I think I bet you have already did this automatic differential. So each of who's the Jacobian matrix of each elementary loads, elementary loads, the Jacobian is exactly known. So the evaluation of the evaluation of the gradient can be just apply the chain rule to each elementary loads, and then we can obtain the gradient. So usually there are two ways to apply the chain rule. One is to apply the chain rule along the computational graph. So this is the forward mode. This means you just apply this chain rule step by step. So this way has just the same order computation cost with the function evaluation, and no need to store the intermediate result. So this method is also very efficient for the computer graph with larger fan out, but less efficient for the larger fan in. So this method is not suitable for the tensor states, because usually tensor states include many input variational parameters, but just the output just a scalar energy. So this method is not this way is not suitable for the tensor network. So there is another way to compute the gradient. This way is the reverse mode AD. They just computed the gradient by the trace back the computational graph, and step by step. Finally, we can obtain the gradient. So this method, but this way we need to store the intermediate result. So we have to store the intermediate result to obtain the gradient. But this way is very efficient for the graph with larger fan in. So this is very suitable for the tensor level states. Later we often use this reverse mode AD to study the tensor level states. And the reverse mode AD is also called the backpropagation in neural networks. And for convenient discussion about below, I will introduce the adjoint of the adjoint concept in reverse mode AD. The inverse, the adjoint of variables is means the derivative of the output respective to the variable x. So if we want to if we want to the gradient, we just pull back the adjoint through the graph. So there are many advantages of the AD has many advantages. But one is the accuracy can up to the machine precision, different from the finite difference, and then the computational cost is the same as the function evaluation. At most, a few factor of the function evaluations, and also support the higher order gradient. And you can also define your own customized parameters such as the SVD, EIG, and QR. And this shows the autograde package. They have defined 200 functions, almost cover the NumPy. As you see in the as you see in the right picture, as you see the backward just a single line, so it's very. And also the loop and conditions or the permutation are all differentiable, and so there also have so far there have many automatic differential tools such as PyTorch we have used, and AutoGrid and Jack's TensorFlow. And also the Flask Zagota are written by the Julia language. But the ADE is faster developing. The tool is faster developing, so there are some many advantage and disadvantage. So for example, the PyTorch can support the GPU accelerate, but not support the complex. So, and the TensorFlow can support the GPU and not support the dynamic graph, computational graph. And the AutoGrid can support the complex, but not support the GPU. So. We usually use the PyTorch and the AutoGrid to, but there have some price if we want to.
Sorry, I have a naive question. Please go back to the previous. What does mean the mixed mode?
Mixed mode is mixed forward and backward.
Oh, I see.
Yeah. And there have some pay price to apply the AD to tensor state. I have mentioned about because in the reverse mode we have to restore the all to store the all intermediate results. So the memory overhead is very large. So. And another possible numerical issue is the SVD or eigensolver instability, and in the first let me first maybe I can fast. So let me first to how to we to reduce the memory. We usually use the checkpoint technique to reduce the memory. This just is a trade-off of time for memory. The idea is divided the computational graph into many small pieces, and in the forward function evaluation, we just store the start point of each pieces, but do not store the intermediate result of the internal pieces. So we just store this load, and without does not support this load. So. And then we in the backward process, if for example, if we want to from this node to this node, because we don't store this intermediate result. So if we want to obtain this result, we have to restart this process, these pieces. So then we can obtain then we can apply the chain rule and obtain this adjoint, this one adjoint. So as you can and then we can continue to this process and go and finally go to the obtain the gradient, and you can say the larger memory is just installed to store this intermediate result. So we can extremely reduce the memory. So and another technique to reduce the memory is to exploit the fixed point equation. I bet you know the tensor algorithms. Usually we have some fixed point equation. For example, for the CTMG method, we have a fixed point equation about the color and edge tensors. So we can use these equations to we can derive the joint of the parameters. So usually the series can very quickly converge. So the memory can just to store this chain. So usually we can reduce the memory.
So typically, how many times do we need?
Usually, for example, for example, in the CTMG, usually we need to several for example, need to 100 times to converge, and this I think just 10 or 20, yeah, just 10 or 20 to converge. So another possible issue is about the SVD or eigensolver, and in the first day, Professor Kawashima asked a question about the AD. So here I try to answer your questions. First, let me first to briefly to how to obtain this equation of the joint. Let me briefly to derive this how to obtain this equation. Maybe this just we can start from this. This just is the chain rule because we want to because if we want to for example, this is the computational graph. This is the A, and this obtain the U and D, and go to the last loss function. So in the backward, we first give the had already loaded this U bar, and the D bar has already known. So this is given, and then we want our goal is to obtain this bar. This is the goal we want to study, and we know this dl partial L is equivalent is equal to partial is partial L partial A and dA. So this is A bar sigma ij sigma ij. So this is you trace this is A bar. So this is A bar T dA. So this is the first the left side, and also you can say the dl is equal to sigma ij partial l partial d and dd, and also plus partial l partial u and du. So this is a right side trace d bar t dd and plus u bar t du. So this is equal to this a bar t dA. So if we want to obtain this one, we should first obtain this equation about the as a function of the dA. So we here we derived the so we used this equation to differentiate this equation and gives this express, and also we can define a matrix DC is equal to U minus du, so that du is equal to U DC, and then this is TDF. So we can obtain this one and multiply the inverse to this two sides and rearrange. We finally obtain this equation. Yeah, this equation is very important. So usually we can say, for example, if the A is symmetry, U minus is U dagger. So usually this DC is anti-symmetric matrix. So the diagonal is 0, and so this you can say that you can say to this side the diagonal element just this one. So we can obtain the DI is equal to this one, and the off diagonal elementary can obtain this. So finally we obtain the DU and DD as a function of DA. So we substituted the DU and DD into this equation. We finally to obtain the as a function of DA. So we finally obtain this the adjoint of A. So is there any questions? So, okay. As you said, this security is defined. This is a Hadamard product. As you see, if the eigenvalue is degenerate, this equation, this equation will become this one. Will become this one, and equal. If the di is equal to dg, this equation has no solution. So this is the problem why the backward is unstable. So in practice, we just introduce a small number equal to lift the degeneracy. Just replace the di dj minus, just input eta, a small eta, and the practical result is very well, but no problem. And then Liao has an argument about why this trick is work. Maybe you can discuss with it. Okay. And this paper is also discuss this problem. This also use this trick. Yeah.
Right question. So by combining this method and the previous memory caching method, so I naively feel that if the recalculation contains some numerical error caused by, for example, the multi-threading calculation or something like the, how to say, eigenvector corresponding degenerate for the corresponding degenerated eigenvalues can be, how to say, can change because of the recalculation. Is that problem actually? So yeah, so if you use a caching technique,
Yeah.
so you may recalculate the SVD, right? And if our implementation contains some multi-threading calculation, then in that case, then how to say, eigenvectors corresponding to degenerated eigenvalues may be different compared with the previous calculation. And so my question is, such kind of situation cause some problems in actual calculation, or sorry. So yeah, so please go back.
Okay.
So yeah, in this caching technique, you repeat some calculation, and if there is some numerical error in the recalculation, the calculation result may change from the previous one.
We applied this trick to study the IC model. I bet you know the IC model is exactly degenerate because they have a Z2 symmetry. So I use this method to study the IC model. We can compute the higher order. For example, this is the first order derivative and the second order derivative. This result is consistent with with the exact solution. I think our trick is very stable.
Okay.
Your question is also related to that one line argument.
Okay.
Because I haven't got a proof for it, but we had this. By the way, Sandro Sorella also had this opinion because he used that like 10 years ago for computing force in his calculation. We had this experience that if the downstream loss function or objective function is gauge invariant, because you see from the analyzation or from SVD, you always have gauge equivalent. But if the loss function is gauge invariant, then actually here in the denominator, there would be some two summations for I and J. But you need to say that only the contributions of I belongs to the occupied space, J belongs to an occupied space will contribute. So that's the same structure as a linear response theory. And if you could construct some quadratic form, which is gauge invariant, you can see this structure. So that means, because your question is related to multi-threading thing, right? Because there was some uncertainty in the determinism. But unless this happens to the energy level that you were doing the truncation, otherwise it doesn't matter. In the occupied space, you can have arbitrary rotation. It won't affect the loss function. Therefore, it won't affect this kind of calculation. That's like argument, suspicion.
Okay. So you overcome these problems. We can use AD to study that to optimize the tensor state. We just tell the computer just how to calculate the error tree, and the computer just can automatically to yield the gradient. So and then we can use the usual optimization methods such as conjugated gradient and Newton method to optimize the tensor state. And so this method is also can apply to any lattice and any Hamiltonian and any contractor schemes. And so let me show you our results. we have use this method to study the square isomorph model. This result is we compared our results with other methods. This method is the simple result, and this is the full update. And the green is the Lawrence result, and red is the Corpus result. So and blue is our result. As you see, in the small d, we just our result is slightly higher than the Corpus result because we just used a single unit cell, and the Corpus used 2x2 unit cell, and we also imposed some symmetry. So and the Lawrence is also used a single unit cell. Yeah. So our result is in the small d is very consistent. And at the larger boundary d, our energy is slightly lower than other results, and also this shows the energy relative area compared to the Sandvik result, the extrapolated result. And this is magnetization.
Sorry, how about state dependency?
Random state.
Convergence iteration.
So
how long needed converge to CTMG?
How long the runtime?
Steps.
Steps. I will show the steps later.
Okay.
You mean this? We just a few hundreds to converge. Yeah. This I will show this result. Yeah, this one. As you see, this study the Kagami has a model. We just we start from the random state, and then just the energy and the magnetism quickly converged just after 100 steps. Yeah. And we also compared with the Sandvik variational RV state. As you see, this is the biased system. And the result at the L equal to 16, the result is this one, and L large, the relative area is slightly higher. So, and we also compare with the variational optimized by the RBM, and as we know, they optimize this result using several weeks. So at this point, 7 point, we just use a single one GPU. I just run 1 week. So.
Why you need a so long time? So I believe that if we perform.
Because I use the CTMG boundary is 160. So because the computational cost of CTMG is proportional to D equal to 12.
Okay.
Yeah. So we use this method to obtain the lowest variation method for the square Hai-Jun model, and we already use this method to study the Kitaev honeycomb model, and this red curve is obtained by the full update method. This is Corpus result, and this blue line is our result. As you see, we just used d equal to 4. Our result is lower than this 7 result, And moreover, the magnetization, our magnetization is almost is very small, but this is finite. So our method can almost capture the Kitaev Japanese spin-equal feature. So we also yesterday Li has shows their results. So here I also compare with their results.
I have a question.
Okay.
Were your computations started from the random state or to obtain this?
Why start from the random state? You mean?
No,
I can start any state. Yeah.
I see.
So this just show our method is very stable. Yeah. And this is the d equal to 4 results. As you see, their result is lower than this the d equal to 4 result, and but slightly higher than our result. And but it is loaded data. They just use one single parameters. Yeah, there here I think I will use I think we use several hundred milli parameters.
700 million? No, this is D.
D equal to 4. Yeah, is 4D qubit. 100. Yeah, 128. Yeah. And this is the D equal to 8 result. They is the slightly lower than our D equal to 6 result. And this is our specific result. As you see, our D equal to 6 result is almost close to this D equal to 8 result. I think we used your version of perhaps to start. I can obtain the slowly noisiest energy. Yeah.
So do you have any comment about the Chi dependence?
Chi in the CTMG usually the energy is go down with the increasing of the boundary chi. Yeah, usually is. Yeah. So if we use larger boundary chi, I think our energy is lower than this one.
Okay.
Yeah, I checked this one. Yeah. So they have also. Yeah.
Help the flux expectation.
You cell?
Flux.
Oh, I don't calculate the flux. Yeah. I think the flux is almost to close to 1 because our energy, the magnetism is very small. I think I do not calculate this one. And I also studied the J1, J2 square Hess model. And on the Monday, Professor Xiang has talked about this, so I will quickly to skip this result. I just show you. Yeah. And maybe you can. We can, as you see, we have we obtained the non-magnetic states without any extrapolation. Yeah, like this. So usual for update usually need to extrapolation with the boundary D. So we just use this method to obtain this without extrapolation.
So how many independent tensors did you use? So the size of unique cell?
I just use 2 by 2 unit cell. Yeah. And this is the variation VPS of the all the parameters, and this is the derivative of of the energy with respect to the J2. I found that so the second phase transition is obviously the first order, and we also found weak first order transition. Maybe this one maybe can continue if we push from dimension D. Yeah.
So this covers also 10 by the AD?
Yeah, this also this calculation alone. This just use the Hellman Feynman-Hellman theorem to calculate this one, because we just because we have loaded this Hellman-Feynman theorem. Hellman-Feynman theorem to because the partial h partial lambda equal to partial partial e partial lambda to partial this. Yeah, this. So we can use this theorem to calculate the first order of respect to the J2. Yeah, this just to compute the next nearest coupling interaction. Yeah. So this is a local term. Just use the derived the AD. And we also because on Monday some people ask about a question. Yeah. So I just show to the calculation results use our recent method. And this is show the energy and the magnetization as a function of the iteration step of the optimization. As you see, we start from the random state and quickly to converged. And our results is, and we compared with our 2017 results of the same public results. As you see, the energy is slightly lower, but the behavior of the as a function of the D is the same. So this convergence is very slowly. This is implied the system is a gapless. So the conclusion is not a change.
So they have a data about magnetization.
Yeah. This show the magnetization. This is the sympathy result, as you see. We just show the 15, d equal to 15, and this is the AD results, and the magnetization is slightly lower than the sympathy results, and also the extrapolation to 0. This magnetization is quickly decrease. Yeah, not like the G1, G2. As you see, the G1, G2 results. This you can say this equal to this one equal to this one, and but in the G1, G2 results. Yeah, the G1, G2 results are just not quickly. Okay. So finally, we also use this method to compute the higher order derivatives. This shows the Ising model. We use the TRG method to contract the partition function, and we compared with the exact solution. This shows the energy. This shows the free energy, and this shows the energy density. By this point is calculated by the AD, and this is exact. And this is the second derivative of the partition function. So as you see, our result is is consistent well with the exact solution. And So let me briefly add. The AD help us to remove the tedious work or to derive the gradient, and let us focus on the algorithms. So in the future, we can apply the AD to other optimization programs in tensor level methods, such as mirror TNR and loop TNR, boundary TRT, isotropic TRT, and forfeit, and other methods. For example, any optimization problem can also use the AD to simplify the problems. We just usually, for example, in the loop TNR, in the previous work, they usually very complex to optimize this one, but here we just take care about the contraction. So we don't need to optimize the so also. Okay, this is my work. So thank you very much. Thank you for listening.
Do you have any comment about the difference between the Kitaev spin-naked state and the Kagome state? So in the case of Kitaev spin-naked, even in the gapless, you obtain the very small or tiny magnetization in the small model dimension. But in the Kagome case, you obtain the slightly larger magnetization for the finite model dimension. What is the difference between two gapless spin-nakeds?
You mean G1, G2 or Kagome?
Kagome.
Because Kagome, we found the energy and the magnetization is converge very slowly. So this implies that we should need a very large dimension to into the converge region. So this implies the ground state. The entanglement of the ground state is maybe have a logarithm correction. So maybe can the entropy will go beyond the error law.
I see.
Maybe I can, because someone proposed the ground state of the Kagome state is U1 direct spin liquid, and because the U1 gauge field will the gauge of excitation is gapless, and the spin-on excitation is also gapless. So maybe the entropy will go beyond the error law. So we need a larger dimension to get the converged result. Yeah.
Thank you.
So from this, the figure is same to
us.
This figure, the ground state energy have not converged.
Yeah.
Even you take the one dimension 8, right?
Yeah. So we have pushed the dimension to be very large.
Do you have the same data for J1, J2, or independence of?
So far, we cannot roll out the spin liquid phase in the G1, G2 model because we just.
Yeah, but my question is the energy.
Yeah.
Function of D.
Maybe here we don't. I can show you all energy results.
Is it better converged as compared to Kagome?
It's maybe this is the energy. This maybe is too not big, so. can. You can help me. Sorry.
You have to just move this direction.
Okay.
So, the ratio different D.
I don't show the maybe I can show this result. Maybe later I can discuss with you. Computer has the.
Usually we have experienced that with increasing D, the convergence is becoming slower.
Yeah,
slower and slower.
Yeah, I can show the parameter, all the parameter with one dimension D. So I can this one, and you can, I can.
Maybe just pay that figure.
Maybe I can show this one. Sorry. This is all. This is a unit cell, and we will use the CTM1G, and this is the derivative. This is all the parameter with one dimension D.
Yeah, how
Energy we done here we will show. We will compare with other method to this 40. No, this is just a 40. I can show. Here I do not show. Maybe I can. Maybe later I can show you our energy with as a function of the normal D.
I wonder, in many cases, with increasing D, convergence becomes slower and slower. So you can put that as a 1/D dependence, but I'm wondering whether the scaling by 1/D is
Okay.
good or not.
From the other parameter, this is also converged. I see. You can see this result is 7, just not converged. You can see this 3 point.
This is what I'm wondering, because with increasing D, whether 1/D port is appropriate or not. Because with increasing D, the convergence becomes very slow. So
yeah, you mean the truncation? We should use the truncation error to do this.
Did you look at the correlation length? Because like in a few recent papers, they show that 1 over the correlation length is actually the right thing to use as an expectation parameter for this. This gap is normal.
Oh, okay.
Do you reach like? Did you look at the correlation length of these states that you obtain?
I do not calculate the correlation.
This is
But the correlation is very difficult to converge with the correlation. Yeah. So we have to extract the correlation.
another suggestion is to see the energy variance, as I mentioned in the morning. If you see the energy variance, if the state is truly improved, then you should see the improvement.
We're going to calculate the invariance, but for the infinite tensor level it is very difficult to calculate the invariance.
In principle, I think you can calculate in a local fashion. The energy variance can be calculated because the Hamiltonian itself is a local.
It's a 2-point function.
This is very difficult.
Well, but for the long range part, it becomes small.
I think the long range part is important.
Yeah, yeah.
in this case?
For the variance,
Maybe.
sure. I
Maybe.
think you can calculate. At least you can see the energy variance with the limited range of
Anyway, the Geometry is very difficult to determine the spin or yeah. Maybe we can discuss on it.
You can apply the automatic differential technique to calculate a higher order differential of partial function. So you can calculate, for example, specific heat. Such technique can be applied to the calculation of variance of you modify the local Hamilton with some.
Yes, we found a method to optimize the calculate the variance, but we have now we don't to compute. We're going to calculate the variance. We found some way to calculate the. But now we don't calculate.
I have one question about your last comment about loop TNR. You said maybe this technique of automatic differentiation can be useful in optimizing this approximation. But do you think whether it is also efficient in removing the entanglement loop? Because I'm asking this because entanglement loop is somewhat topological object. So once such a topological object is formed, then maybe it is difficult to remove such a loop by.
Yeah, you mean loop TNR contains two steps. One is the remove the shorter range entanglement, and the second is optimize this one. So you mean how to remove the first entanglement, short entanglement? Your question is
not really. Well, in some sense it's short entanglement, but it is loop.
We just simplify this problem. I think our method is equivalent this we just simplify, not new algorithms.
I see. So if the original algorithm solves this problem, then there is no reason that this.
We just simplify the optimization problem, not.
We can consider about penalty term, which correspond to some entanglement in the loop. If we such an objection function to construct the minimum entanglement solution, so we can use this technique. Usually we only consider the norm, but in such case, some local minimum, there are many, probably local minimum. Some local minimum contain a shorter.
So you are saying that this is not just this is not just a simple gradient descent gradient method with this cost function. It is more than that in many ways.
Plus penalty represent
yes.
amount of
that's right. Maybe that's why.
Yeah. If you use AD, you can see we can apply this is this 8 tensor is equal 1. Yeah. So this problem is a non-linear problem. Yeah. We can also use our AD to solve this problem. But if you use other, you have to use the alternate nearest square method to solve. I think this is the advantage of AD. Yeah, we have already tried this one. Yeah. This is work.
So in practice, how many initial states did you consider So I know it's a variational method, so it doesn't have to get trapped in local minimum. But how many initial states?
I usually initial to random state.
Just one state? Or several, maybe considering 10 or 20 initial states and pick up the lowest energy states?
Usually, for example, if you optimize this one, we usually we can choose the SVT to the initial. Usually, if we choose a good initial, we can very quickly to converge. But if we choose a better initial, the initial state, the runtime is.
Okay, thank you very much again.